Morning everyone, my name is Amauri from University of Brasilia, Brazil. I will present this work entitled Inductive Interferences between a 500 kV power line and a pipeline with a complex approximation layout and multilayered soil. My colleagues in this research are Caio Moraes from University of Brasilia and Dr. Felipe Lopes from Federal University of Paraíba, Brazil. Here's our agenda. We will start with a brief description of the basic EMI mechanisms, describe our simulation model, then we move on to the simulation results and present our conclusions. This picture describes the context in which we are inserted. Different facilities such as pipelines, power lines, railways often share the same space, which may cause electric interferences caused by inductive, capacitive, and conductive coupling mechanisms. Inductive coupling is a magnetic field effect caused by the current flow through the line conductors, in the presence of an interfered structure. The electromagnetic interaction causes the rise of voltages along the pipeline, which may lead to potentially harmful effects such as touch and stress voltages. Inductive coupling is affected by a variety of effects, but in special the exposure, geometry, and the soil resistivity. This is the system we aim to study. The pipeline follows this winding path and crosses the transmission line path here with an exposure length of 4 km. It is a 500 kV transmission line with a cross-section given here. The soil model is determined from measurements performed at each tower location and results in this structure with 3 layers shown here. One challenge is to construct a circuit model able to properly represent the complex coupling geometry. This is achieved by subdividing the affected pipeline into coupling regions represented by these numbers here. Each coupling region is then modeled as an equivalent parallel section. Essentially, we define two distances d1, d2 inside the coupling region, and we compute the equivalent parallel parameters as shown here in these equations. The resulting circuit is shown in this figure, in which we have 7 coupling regions modeled in the ATP as line constant objects using the nominal pi circuit model. The crossing between the pipeline and the power line occurs here at section 4. The effects of the pipeline coating are introduced by means of these resistors and these capacitors shown here. Transmission line grounding are modeled by using these resistors at the extremity of each section as shown here in these figures. Now, the problem with the soil is that the ATP line constants routine is based on the original Carson's equation for a uniform soil model. So, if you double-click this line constants object here, you will notice that the program expects a single real-valued resistivity parameter. So, how to model our 3-layered soil? We have used a strategy to represent the multi-layered soil structure in terms of a uniform equivalent. By means of this relatively simple recursion formula, we can obtain an equivalent resistivity parameter that can be used with the LCC. To validate our simulations, we have compared the voltage profile along the pipeline with software CDEX, which effectively accounts for multilayered soils. All the parameters are shown here. We can see that there is a very good agreement between the curves with an RMS error of less than 8% between the proposed method and CDEX, and we have an excellent fit at the crossing location where we see that the voltage reached the minimum value. Here we have different soil models. Here we have the parameter as given under IEEE STD80, which is essentially the arithmetic mean of the apparent resistivities. And here we have the uniform soil model obtained using CDEX, which is based on the curve fitting technique. Based on the curves, we can see that larger resistivity values result in increased voltage levels at the pipeline extremities. With 41 volts by using the proposed method, 48 volts if you consider the STD80 uniform model, 47 volts if you consider the reset uniform soil models, and finally 39 volts being the value corresponding to the actual layered soil structure. These values exceed the safety limit of 15 volts, which may require corrective actions. To mitigate these large AC voltages shown over here, one possible strategy is to ground the pipeline at the extremities using a DC decoupler, which is this device here. The device is connected to the pipeline and to a properly designed grounding system, which could be a bare copper conductor laid in parallel with the pipeline. The situation can be easily simulated using the proposed circuit model by setting these resistors here to a low value, let's say 0.1 ohm. Then we can see that induced voltage levels are reduced from 41 to about 10 volts, which is more than 75% decrease, and thus observing the safety standards, mitigating risks of unwanted touch voltages and eventually corrosion caused by AC. So, in conclusions, you have that the proposed approach is accurate with RMS error of less than 8%. It is fast, requiring less coupled P cells, and is able to carry out simulations with or without mitigation devices. We notice that profiles agree with industry standard software and previous literature reports. We managed to observe the prevailing effect of the deepest soil layer. We also notice that induced voltages increase with the soil resistivity, and that by means with appropriate grounding systems we managed to reduce the interference voltage levels in 75%. These circuit models open a broad range of new research possibilities. Since everything is based on the ATP model, we can carry out time domain simulations of power system transients, fault studies, lightning discharges, and others. So, thank you for your attention.